Look up into the night sky, and you are staring directly into an ocean of infinite scale, an overwhelming expanse that challenges every perception of reality we hold on Earth. The universe is not merely a collection of stars and planets scattered across space. It is a dynamic, evolving cosmos governed by the laws of physics, stretching far beyond what our eyes or even our most powerful telescopes can observe. Across this vast cosmic web, trillions of galaxies drift through an ever-expanding void, each containing billions of suns, mysterious worlds, and high-energy phenomena that defy imagination. From the searing cauldrons of stellar cores to the silent, invisible pull of supermassive black holes, the cosmos operates on scales of distance and time so colossal that human experience is but a fleeting moment within it. Yet through science and observation, we have developed the tools to decipher its history, chart its geometry, and understand the fundamental forces that shape every atom of our existence. We are composed of the very matter created inside ancient cosmic explosions, making our quest to comprehend the universe a journey of self-discovery. Today, we begin an unforgettable journey through the universe. If you enjoy exploring the deep mysteries of space, please feel free to like this video, subscribe to the channel, and leave a comment below sharing exactly where on Earth and at what time you are watching this today. Our cosmic story begins not in the deepest reaches of intergalactic space, but right here in our immediate neighborhood, where a brilliant yellow dwarf star binds a collection of worlds in a relentless gravitational dance. At the center of everything lies the Sun, an immense sphere of glowing plasma containing over 99% of all the mass in the entire solar system. Deep within its core, gravitational pressure reaches levels so extreme that hydrogen nuclei fuse into helium through nuclear fusion, a process occurring at temperatures exceeding 15 million degrees Celsius. Every single second, the Sun converts over 4 million tons of matter directly into energy, radiating power across the electromagnetic spectrum and blasting a constant stream of charged particles called the solar wind out toward the stars. This violent engine creates an immense bubble known as the heliosphere, shielding our planet and its neighbours from the harsh cosmic rays of deep space, while simultaneously dominating the environment of every world within its reach. Moving outward from this raging furnace, we encounter the inner rocky planets, worlds shaped by extreme heat, crushing atmospheric forces, and ancient volcanic activity. The closest of these is Mercury, a battered and airless world orbiting extraordinarily close to the stellar fire. Because Mercury lacks a thick atmosphere to retain heat or distribute thermal energy around its surface, it experiences some of the most dramatic temperature swings anywhere in the solar system. During the scorching daylight hours, the surface bakes under unrelenting solar radiation, climbing to temperatures exceeding 400 degrees Celsius, hot enough to melt lead. Yet, as night falls across its cratered landscape, that heat escapes instantly into the cold vacuum of space, causing temperatures to plunge below -170 degrees Celsius. Further out lies Venus, a world often described as the twin of Earth in terms of size and mass, but one that evolved into a hellish, hostile landscape. Venus is wrapped in a dense, suffocating atmosphere composed almost entirely of carbon dioxide, topped with thick clouds of sulfuric acid that permanently obscure its surface from view. This massive atmospheric blanket creates a runaway greenhouse effect of terrifying proportions. Thermal energy from the Sun passes through the upper atmosphere but becomes trapped beneath the dense carbon dioxide layer, driving surface temperatures up to an average of 465 degrees Celsius. This makes Venus the hottest planet in the entire solar system, even hotter than Mercury, despite being nearly twice as far from the Sun. Worse still, the atmospheric pressure at the surface is 90 times greater than that of Earth, equivalent to the crushing pressure experienced nearly 1 kilometre beneath Earth's oceans. Any probe sent to land on Venus faces a brutal combination of metal-melting heat, corrosive acid clouds, and mountain-crushing pressure. Beyond Earth's habitable sanctuary lies Mars, the iconic red planet, a frozen desert world that presents a stark contrast to the burning pressures of Venus. Mars derives its signature rust-red hue from iron oxide dust coating its dry, barren surface. Unlike Venus, Mars possesses an extremely thin atmosphere composed mainly of carbon dioxide, providing less than 1% of Earth's atmospheric pressure. Because of this thin air, Mars cannot retain heat, resulting in a frigid global climate where average temperatures hover around -60 degrees Celsius. Despite its current barren state, the Martian landscape bears clear geological scars from a much more dynamic past. Giant dry river valleys, ancient lake beds, and massive flood channels carved into the crust indicate that liquid water once flowed abundantly across its surface billions of years ago. Mars is also home to some of the most extraordinary geological structures in the solar system. Rising high above the dusty plains is Olympus Mons, a colossal shield volcano 3 times the height of Mount Everest and wide enough to cover the entire state of Arizona. Nearby lies Valles Marineris, an immense canyon system stretching thousands of kilometers across the planet's equator, dwarfing Earth's Grand Canyon in both depth and length. Today, stable liquid water cannot persist on the Martian surface due to low atmospheric pressure, which causes ice to sublimate directly into gas when warmed. However, vast reserves of water ice remain locked within the polar ice caps and trapped beneath the dusty soil as permafrost. The dramatic transformation of Mars from a warm, wet world with a thick atmosphere to a cold, dry desert remains one of the most compelling mysteries in planetary science, serving as a reminder of how delicate the balance of habitability can be. Venturing beyond the inner solar system, past the dense rubble of the asteroid belt, we cross the frost line and enter the realm of the gas giants, where vast worlds of hydrogen, helium, and ice dominate the darkness. The transition is marked by Jupiter, the undisputed monarch of our solar system. Containing more than twice the combined mass of all other planets put together, Jupiter acts as a gravitational anchor, shaping the orbital paths of countless asteroids and comets. This planetary colossus lacks a solid surface altogether. Instead, its atmosphere transitions gradually into a dense, metallic ocean of fluid hydrogen under immense core pressure. Jupiter is famous for its striking bands of swirling clouds, driven by ferocious winds exceeding 600 kilometers per hour. Within these turbulent cloud decks sits the Great Red Spot, a colossal anticyclonic storm larger than planet Earth that has raged continuously for centuries. Yet, Jupiter's most intriguing features lie in its vast family of moons. Europa, a smooth, ice-covered moon, hides a global liquid ocean beneath its frozen crust, containing more water than all of Earth's oceans combined. Warmed by internal tidal friction caused by Jupiter's intense tidal flexing, Europa's subsurface ocean is considered one of the most promising environments in the search for extraterrestrial life. Beyond Jupiter orbits Saturn, a stunning jewel surrounded by the most spectacular ring system in the solar system. Spanning hundreds of thousands of kilometers across, but measuring only tens of meters thick, these luminous rings are composed of billions of individual particles of pure water ice and rocky debris. Like Jupiter, Saturn is a gas giant dominated by hydrogen and helium, featuring high-speed atmospheric jet streams and a mysterious hexagonal storm spinning around its north pole. Saturn also hosts remarkable worlds among its many moons. Titan, the second largest moon in the solar system, is wrapped in a thick, nitrogen-rich atmosphere denser than Earth's, complete with weather systems, clouds, and rainfall. However, Titan's rivers and lakes are filled not with liquid water, but with liquid methane and ethane flowing at -180 degrees Celsius. Meanwhile, the tiny ice moon Enceladus shoots massive geysers of water vapor, organic molecules, and simple salts directly into space through deep fissures at its south pole, offering direct evidence of another warm, habitable subsurface ocean beneath its icy shell. Further out into the cold shadows dwell the ice giants Uranus and Neptune, worlds rich in water, ammonia, and methane ice. Uranus is an enigmatic giant, tilted so far on its side that its axis of rotation lies almost parallel to its orbital path, causing extreme 84-year seasonal cycles unlike anything else in the solar system. Its dynamic atmospheric winds are subtle, yet its soft cyan hue radiates a quiet beauty. Neptune, the outermost major planet, appears as a vivid deep blue sphere battered by the fastest winds recorded in the solar system, reaching speeds of over 2,000 kilometers per hour. Its massive moon Triton orbits in a retrograde direction, indicating it was once an independent dwarf planet captured by Neptune's gravity. Triton features active cryovolcanoes that spout liquid nitrogen geysers into space, proving that even at the edge of the planetary zone, geological activity persists. Beyond the orbit of Neptune lies the Kuiper Belt, a vast donut-shaped region of primordial ice, rocks, and dwarf planets remaining from the formation of the solar system. Here resides Pluto, a complex world with icy mountains, vast nitrogen plains like Tombau Regio, and a thin atmosphere. Alongside Pluto are other dwarf planets like Eris, Haumea, and Makemake, cold sentinels lingering in the deep freeze of space. Surrounding this entire outer structure at the farthest edge of the Sun's gravitational dominance sits the Oort cloud. This hypothetical spherical cloud of trillions of icy cometary bodies extends up to 100,000 astronomical units from the Sun, reaching almost halfway to the nearest star. The Oort cloud marks the ultimate boundary of our solar neighbourhood, a dark and distant reservoir of ancient ice, waiting to begin a long journey toward the stellar fire. Leaving behind the cold fringes of the Oort cloud, we break free from our home star's influence and venture out into the vast, uncharted territory of interstellar space. For thousands of years, humanity could only wonder if other suns hosted worlds of their own. Today, modern astronomy has unlocked the doors to thousands of alien exoplanets, revealing a cosmos far more diverse, chaotic, and bizarre than anyone ever imagined. These distant worlds challenge our traditional models of planetary formation, proving that nature creates environments far beyond the wildest realm of science fiction. Among the most extreme worlds discovered are the scorching lava planets, celestial hellscapes orbiting so shockingly close to their parent stars that their surfaces are literally melted into global oceans of liquid rock. Consider worlds like 55 Cancri E or Kelt 9b. On 55 Cancri E, an exoplanet over 8 times more massive than Earth, the day side is permanently locked facing its host star due to extreme gravitational forces. Temperatures on this perpetually sunlit hemisphere reach nearly 2,500 degrees Celsius. At these unfathomable heat levels, the rocky surface liquefies into an endlessly churning ocean of molten lava under a thin atmosphere of vaporized minerals. On the planet's night side, which never sees stellar light, temperatures drop precipitously, causing the evaporated rock in the atmosphere to condense and rain down as solid stone. Even more shocking are the ultra-hot Jupiters like Kelt 9b, a giant planet orbiting a star so hot that the planet's atmospheric temperatures exceed 4,300 degrees Celsius. This is hotter than the surfaces of most stars in the galaxy. At these extreme temperatures, heavy molecules like water vapor, carbon dioxide, and methane cannot hold themselves together. They are ripped apart into their constituent atoms by the relentless thermal energy, while vaporized iron and titanium float through its glowing sky. In stark contrast to these dense liquid rock infernos are the ultra-low-density exoplanets known as superpuffs, or cotton candy planets. Worlds like Kepler 51b and Kepler 51c challenge everything planetary scientists thought they understood about density and gravity. These planets are roughly the size of Jupiter, spanning tens of thousands of kilometers across, yet their total mass is only a few times that of Earth. Their average density is astonishingly low, less than 1/10 of a gram per cubic centimeter, lower than that of cotton candy or styrofoam. If you could somehow place one of these superpuff planets into a gigantic ocean of water, it would float like a feather on the surface. These worlds are wrapped in immensely inflated atmospheres of hydrogen and helium gas, expanded to absurd proportions by internal heat and energy from their young parent stars. Scientists believe these planets are rapidly leaking their gaseous envelopes into the void, evolving over millions of years from swollen, airy giants into much smaller, denser cores. The alien spectrum continues to astound with worlds made of exotic matter under extreme pressure. In planetary systems rich in carbon rather than oxygen, high internal pressures can transform deep subterranean layers into solid diamond, creating worlds with mantle structures composed of glittering gemstones. Elsewhere, Astronomers have detected ocean worlds completely covered by global water layers hundreds of kilometers deep, lacking any solid land or continents whatsoever. Deep beneath these global waters, the pressure is so intense that the water molecules are squeezed into exotic, high-density crystalline structures known as Ice 7 and Ice 10, which remain solid even at burning temperatures. We also find hot Neptunes orbiting dangerously close to their stars, where the intense radiation strips away their outer gas layers, leaving behind long, glowing tails of hydrogen gas that stretch for millions of kilometers through space like celestial comets. There are worlds orbiting binary star systems, where two suns rise and set over the horizon every single day, creating complex gravitational dances that alter the weather and seasons in unpredictable ways. The discovery of these strange exoplanets forces us to abandon our solar system-centric views of cosmology. Each new world reveals a different outcome of the chaotic forces that govern planetary evolution. From skies that rain molten iron to puffy worlds suspended like clouds in space, the variety of exoplanets shows that our solar system is just one specific recipe among an endless cosmic menu. While the universe is filled with billions of planets bound to the light and heat of their host stars, there exists a darker, more solitary class of worlds roaming the cosmic abyss. These are the rogue planets, also known as free-floating or nomad planets. Ejected from their original stellar systems during the violent gravitational chaos of early planetary formation, these untethered worlds were cast out into the eternal, freezing darkness between the stars. Without a sun to illuminate their skies or warm their surfaces, rogue planets drift endlessly through the interstellar medium, silent and unseen shadows navigating the vast Milky Way galaxy. Astronomers estimate that rogue planets may actually outnumber the bound stars in our galaxy by trillions. Despite the absolute cold of deep space, where temperatures hover near absolute zero, many of these sunless worlds are far from dead. Beneath their frozen outer crusts, rogue planets can retain significant amounts of geothermal energy left over from their formation, supplemented by the continuous decay of radioactive elements within their rocky cores. If a rogue planet is large enough, or if it possesses a thick blanket of molecular hydrogen gas, it can trap this internal heat effectively. In some remarkable cases, this thermal retention allows liquid water oceans to persist beneath miles of solid surface ice for billions of years, creating pitch-black subterranean biospheres that exist completely independent of stellar light. Yet, as we peer into the darkness for these lonely wanderers, humanity's ultimate quest in exoplanet exploration remains the search for worlds that mirror our own, planets orbiting within the circumstellar habitable zone, informally known as the Goldilocks zone. This is the precise orbital region around a star where conditions are neither too hot nor too cold, but just right for liquid water to exist stably on a planet's surface. Water is the universal solvent, the essential medium through which organic chemistry can react, assemble, and evolve into life. Identifying a planet within the Goldilocks zone is only the first step in determining its true habitability. A star's nature dictates where its habitable zone lies. Around smaller, cooler red dwarf stars, which make up over 70% in all stars in the galaxy, the habitable zone is squeezed extremely close to the star. While red dwarfs burn their fuel efficiently and can live for trillions of years, their close-in habitable zones present severe challenges. Planets orbiting close to red dwarfs often become tidally locked, meaning one side of the planet permanently faces the star in perpetual daylight, while the other side is frozen in eternal night. Furthermore, young red dwarfs frequently unleash violent magnetic flares and energetic coronal mass ejections that can strip away planetary atmospheres over time. Despite these harsh conditions, systems like TRAPPIST-1 give scientists tremendous hope. Located 40 light-years away, TRAPPIST-1 is an ultra-cool red dwarf star orbited by 7 Earth-sized rocky planets, 3 of which reside squarely within the star's habitable zone. Atmospheric studies using advanced space telescopes are currently analyzing the chemical signatures of these distant skies, searching for biosignatures such as atmospheric water vapor, carbon dioxide, oxygen, ozone, and methane. To determine whether a world within the habitable zone can actually support life, scientists look beyond mere distance from a star. A planet may benefit from a protective magnetic field generated by a molten rotating core to shield its surface from destructive cosmic radiation and solar winds. It also needs a balanced carbon cycle and a stable atmosphere with sufficient density to regulate surface temperatures through a mild greenhouse effect without spiraling into a runaway inferno like Venus. The search for Earth-like worlds has expanded to include super-Earths, rocky planets larger than Earth but smaller than ice giants like Neptune. With stronger gravitational pulls, super-Earths can hold on to thicker atmospheres and maintain active internal geological dynamics for longer periods, potentially making them even more hospitable to life than our own planet. As observational technologies advance, detecting liquid oceans, seasonal weather changes, and chemical markers of life on worlds light years away transitions from the realm of imagination into achievable empirical science, bringing us closer to answering the ultimate question: are we alone in the universe? Beyond the planetary systems and lonely rogue worlds lies the engine of cosmic evolution, the birthplace of stars themselves. Deep within the spiral arms of galaxies, floating through the cold vacuum of space, are vast interstellar structures known as giant molecular clouds. Stretching across tens or even hundreds of light years, these massive cosmic clouds consist predominantly of cold molecular hydrogen gas, helium, and fine particles of microscopic stardust. These regions, often referred to as stellar nurseries, are the cold cradles where every sun in the universe is born. Within these clouds, temperatures plummet to just a few degrees above absolute zero, creating a quiet environment where thermal motion slows down enough for subtle physical forces to alter the fabric of space. For millions of years, a molecular cloud can remain in a delicate state of hydrostatic equilibrium, where the outward pressure of the gas balances the inward pull of its own cumulative gravity. However, this fragile stability cannot last forever. The equilibrium is inevitably disrupted by external shock waves radiating through the interstellar medium. These disruptions can be triggered by the violent explosion of a nearby dying star in a supernova, the energetic shock waves from newly formed massive stars, or the colossal gravitational compression caused by the movement of galactic spiral arms. When a shock wave collides with a cold molecular cloud, it compresses the gas and dust, breaking the uniform density and creating localized regions of higher mass. Once a region within the cloud achieves a critical threshold of density, known as the Jeans mass, gravity takes complete control. The local gravitational force overcomes the gas pressure, initiating a runaway gravitational collapse. As gravity draws matter inward from all directions, the cloud fragments into smaller, dense pockets of collapsing material. Each collapsing fragment begins to draw in surrounding gas and dust at an accelerating pace. As this matter falls inward toward the center of mass, gravitational potential energy is converted directly into thermal kinetic energy. The collapsing core warms up, dense dust grains trap the generated thermal energy, and a protostar begins to take shape in the dark heart of the cloud fragment. During this early protostellar phase, the object is not yet a true star, as nuclear fusion has not commenced. The protostar continues to feed on the surrounding gas cloud, accreting material through a vast circumstellar disk of gas and dust that forms around its equator. Due to the conservation of angular momentum, any initial spin of the collapsing cloud fragment amplifies as it shrinks, causing the surrounding material to flatten into a spinning accretion disk. While most of the disk's mass falls onto the central protostar, intense magnetic fields threading through the spinning disk channel a fraction of the infalling matter away from the equator. This material is ejected perpendicular to the disk in spectacular, highly collimated supersonic jets of ionized gas that blast out into space for light years. These powerful outflow phenomena, known as Herbig-Haro objects, clear away the surrounding dust envelope, carving out vast cavities in the parent molecular cloud. As the protostar grows in mass, the gravitational pressure at its core escalates dramatically. The core contracts further, driving internal temperatures up into millions of degrees Celsius. The matter within the core transforms into a dense plasma, where atoms are stripped of their electrons. Under these extreme conditions, positively charged hydrogen nuclei, or protons, are forced into extremely close proximity. Ordinarily, electrostatic repulsion, the electromagnetic force that causes like charges to repel, would prevent protons from touching. However, when core temperatures reach roughly 10 to 15 million degrees Celsius, the kinetic energy of the protons becomes immense. Quantum tunneling allows these protons to overcome the repulsive electrostatic barrier, bringing them within range of the strong nuclear force, the most powerful fundamental force in nature over microscopic distances. At this critical threshold, nuclear fusion ignites. 4 hydrogen protons fuse together through a multi-step sequence known as the proton-proton chain reaction, forming a single, stable helium nucleus. Because the mass of the resulting helium nucleus is slightly less than the combined mass of the 4 original protons, the missing mass is converted directly into energy according to mass-energy equivalence. This energy is released in the form of high-energy gamma-ray photons and particles called neutrinos. The intense radiative pressure produced by this nuclear fusion rushes outward from the core, pushing back against the unrelenting inward pull of gravity. When the outward thermal and radiative pressure perfectly balances the inward gravitational collapse, the newly born star achieves hydrostatic equilibrium. At this precise moment, the protostellar phase ends, and a main sequence star is born. The newborn sun ignites with brilliant light, blowing away the remaining circumstellar accretion disk with a fierce stellar wind and illuminating the surrounding gas cloud. Famous stellar nurseries, such as the Pillars of Creation in the Eagle Nebula or the vast Orion Nebula, show this process in action today, where towering columns of gas are sculpted by the radiation of infant stars. The initial mass of the collapsing protostellar core determines the entire destiny, color, temperature, and lifespan of the star. Low-mass stars, such as red dwarfs, consume their hydrogen fuel at an incredibly slow rate, allowing them to shine steadily for hundreds of billions or even trillions of years. Medium-mass stars, like our Sun, burn through their fuel over roughly 10 billion years. Classic stars, tens or hundreds of times more massive than the Sun, burn with scorching blue heat and consume their hydrogen reserves at a furious pace, living short, dramatic lives that last only a few million years. Through this continuous process of cloud collapse, disk accretion, and nuclear ignition, the universe endlessly recycles interstellar material, turning dark clouds of cold gas into the bright engines that illuminate the cosmos. Every star, no matter how bright or massive, must eventually face an inevitable energy crisis when its nuclear fuel runs dry. A star lives in a constant tug-of-war between the inward pull of gravity and the outward radiative pressure generated by nuclear fusion in its core. For millions or billions of years, this balance holds firm. However, when the central supply of hydrogen fuel in the core is completely exhausted, fusion slows down, gravity regains the upper hand, and the star begins its final dramatic transformation toward death. For medium-mass stars like our Sun, the end is a long, elegant fade. As hydrogen in the core runs out, the core contracts under gravity, generating intense heat that ignites a shell of hydrogen fusion around the spent center. This sudden surge of energy forces the outer layers of the star to expand outward by hundreds of times, turning the star into a bloated red giant. Eventually, the core grows hot enough to fuse helium into carbon and oxygen through the triple alpha process. Once helium is exhausted, the star lacks the mass needed to reach the core pressures required to ignite carbon fusion. The unstable outer layers are blown away into space in a series of thermal pulses, creating a glowing, colorful shell of expanding gas known as a planetary nebula. At the heart of this nebula sits the dead core of the star, a white dwarf. A white dwarf is an extremely dense object, roughly the size of Earth but containing the mass of the Sun. It no longer generates energy through fusion. Instead, it is supported against gravitational collapse by electron degeneracy pressure, a quantum mechanical phenomenon where electrons resist being squeezed into the same quantum state. Over hundreds of billions of years, white dwarfs slowly radiate away their heat into the cold vacuum of space, eventually cooling into dark, inert black dwarfs. For massive stars, those with masses 8 times greater than the Sun or more, The end is not a gentle shedding of gas, but an apocalyptic explosion. These supergiant stars burn through their nuclear fuel at a furious pace. After fusing hydrogen into helium, their extreme core pressures allow them to fuse progressively heavier elements in successive layers like an onion. Helium into carbon, carbon into neon, neon into oxygen, and oxygen into silicon. Each fusion stage yields less energy and lasts for a shorter duration, culminating in the synthesis of iron in the central core. Iron is the ultimate nuclear dead end. Fusing elements lighter than iron releases net energy, but fusing iron atoms consumes energy rather than producing it. When the stellar core fills with iron, nuclear fusion halts abruptly, eliminating the outward thermal pressure that held gravity at bay. In less than a single second, the star's immense mass crushes the core. The gravitational pressure becomes so extreme that electrons and protons are forcibly crushed together, combining to form neutrons and releasing a flood of ghost-like particles called neutrinos. The collapse of the core continues until it hits the repulsive force of the strong nuclear force and neutron degeneracy pressure. The core becomes an impenetrable, hyperdense sphere of solid neutrons, abruptly halting the collapse. The infalling outer layers of the star, crushing downward at a significant fraction of the speed of light, slam into this unyielding nuclear surface and bounce violently outward. Driven by this physical rebound and an overwhelming wave of energetic neutrinos, a catastrophic shockwave rips through the star, tearing it apart in a core collapse supernova explosion. For a few brilliant weeks, a single supernova can shine with the luminosity of an entire galaxy of billions of stars combined. The extreme temperatures and massive neutron flux generated during the supernova explosion trigger rapid neutron capture nucleosynthesis, also known as the R process. It is within these violent cosmic explosions that the universe creates elements heavier than iron, including gold, platinum, silver, and uranium. Every heavy element on Earth, including the metals in our technology and the iron in our blood, was forged in the fiery deaths of ancient massive stars. The remnant left behind in the wake of a supernova depends entirely on the original mass of the dying star. If the remaining core mass is below 3 times the mass of the Sun, the core survives as a neutron star. A neutron star is one of the most extreme objects in the universe, packing more mass than the Sun into a sphere only 20 kilometers in diameter. A single teaspoon of neutron star material would weigh over 1 billion tons on Earth. Many neutron stars spin rapidly, rotating hundreds of times per second due to the conservation of angular momentum as the massive stellar core shrank down to a tiny radius. These rapidly spinning, highly magnetized neutron stars are known as pulsars. Pulsars funnel high-energy particle beams out from their magnetic poles, emitting focused streams of electromagnetic radiation across the spectrum. As the star rotates, these beams sweep through space like a cosmic lighthouse. When these beams cross Earth's line of sight, astronomers detect extremely precise, rhythmic pulses of radio waves or X-rays. However, if the mass of the collapsing stellar core exceeds the Tolman-Oppenheimer-Volkoff limit, roughly 3 times the mass of the Sun, no force in known physics can halt the gravitational collapse. Neutron degeneracy pressure fails and the material collapses past the threshold of space and time, plunging toward a point of infinite density and giving birth to a black hole. Through these magnificent cycles of stellar death, stars return their enriched chemical elements back into the interstellar medium, seeding the gas clouds that will form future solar systems, planets, and life. Among all the celestial phenomena created by the death of massive stars and the evolution of galaxies, none challenge our fundamental understanding of physics more than black holes. A black hole is not a hollow void or a vacuum cleaner sweeping through space, but rather a concentration of mass so dense that its gravitational pull bends space and time beyond their breaking points. When a massive star collapses under its own weight, or when vast clouds of gas condense in the early universe, matter can be squeezed into a region of zero volume and infinite density known as a gravitational singularity. At this singular point, the equations of general relativity break down, and our current understanding of physics reaches its absolute limit. Surrounding the central singularity is a mathematical boundary known as the event horizon. The event horizon is the point of no return. It represents the precise radius where the escape velocity required to break free from the black hole's gravitational grip equals the speed of light. Because nothing in the universe can travel faster than light, anything that crosses this invisible threshold, whether it is gas, dust, stars, or photons of light, is permanently trapped inside. From outside the event horizon, no information or signals can ever escape, rendering the interior forever invisible to the observable universe. The physical radius of this horizon is directly proportional to the black hole's mass, a distance defined as the Schwarzschild radius. As matter approaches the event horizon of a black hole, it experiences gravitational forces that warp the surrounding environment in extraordinary ways. Matter falling toward a rotating black hole does not plunge directly inside. Instead, it settles into a rapidly spinning structure called an accretion disk. Friction, intense gravity, and magnetic forces within the accretion disk heat the infalling gas to tens of millions of degrees Celsius, causing it to glow brilliantly in X-rays and gamma rays before slipping past the horizon. Furthermore, intense gravitational field gradients near a black hole produce severe tidal forces. An object falling into a stellar mass black hole experiences a dramatic difference in gravitational pull between its leading edge and its trailing edge, stretching the material vertically and compressing it horizontally in an extreme physical process called spaghettification. While stellar mass black holes form from individual dying stars, the cosmos also hosts supermassive black holes containing millions or even billions of times the mass of our Sun. These giant monsters reside at the centers of almost every large galaxy, including our own Milky Way. When a supermassive black hole actively feeds on massive quantities of surrounding gas, dust, and disrupted stars, it transforms the center of its host galaxy into an active galactic nucleus, the most luminous engines in the universe, known as quasars. Quasars, short for quasi-stellar radio sources, were most common in the early universe, billions of years ago, when galaxies were young and rich in chaotic interstellar gas. As colossal amounts of matter fall toward the central supermassive black hole of a quasar, the accretion disk becomes superheated to unimaginable levels. The gravitational energy of the infalling matter is converted into electromagnetic radiation with astonishing efficiency, far outshining the combined light of all the hundreds of billions of stars in the host galaxy around it. A single quasar can shine hundreds of times brighter than the entire Milky Way, while operating within a volume no larger than our own solar system. The mechanics of a quasar involve complex interactions between extreme gravity, fluid dynamics, and magnetic fields. As gas swirls within the relativistic accretion disk, magnetic field lines become tightly wound and twisted, like a spring, by the spin of the central black hole and the disk itself. These powerful magnetic fields channel a fraction of the infalling ionized gas away from the event horizon before it can cross the threshold. The energetic plasma is accelerated along the black hole's axis of rotation to velocities approaching 99% of the speed of light, blasting outward into intergalactic space in narrow, highly focused relativistic jets. These relativistic jets can stretch for hundreds of thousands of light years, slicing through the host galaxy and extending far into the intergalactic medium. As these high-energy particle beams collide with surrounding gas clouds, they shock the gas, triggering radio emission and sweeping away interstellar material. This process, known as active galactic nucleus feedback, plays a critical role in controlling galactic evolution. By blowing away the raw gas needed to form new stars, powerful quasars can effectively shut down star formation throughout their host galaxies, regulating the growth and life cycle of entire cosmic structures. In the early universe, quasars served as luminous cosmic beacons, their intense ultraviolet radiation helping to reionize the neutral hydrogen gas filling space during the cosmic dawn. Observing distant quasars today allows astronomers to look back in time billions of years, studying the conditions of the early cosmos when galaxies were first assembling. Through these energetic powerhouses, supermassive black holes demonstrate that even the darkest, most destructive phenomena in space act as fundamental architects of galactic structure. Beyond the event horizons of supermassive black holes, lie other cosmic entities that push the extreme laws of physics to their absolute breaking points. Among the most violent and magnetized objects in the cosmos are magnetars, a rare and highly specialized subspecies of neutron stars. Born from the fiery deaths of massive stars in supernova explosions, magnetars possess magnetic fields of incomprehensible strength. While a typical neutron star boasts a formidable magnetic field, a magnetar generates a magnetic field up to 1,000 times stronger, reaching intensity levels exceeding 100 billion Tesla. To put this into perspective, a magnetar's magnetic field is trillions of times more powerful than Earth's geomagnetic field and millions of times stronger than any magnetic field ever produced in human laboratories. The physical consequences of such a powerful magnetic field are staggering. If a magnetar were situated halfway to the Moon, its magnetic flux would erase the magnetic data from every credit card on Earth and instantly warp the atomic structures of all matter within range. Under these magnetic forces, electron orbitals around atomic nuclei are compressed into ultra-thin, needle-like cylinders, fundamentally altering chemical bonding and atomic interactions. The magnetic field exerts such immense pressure on the ultra-dense physical crust of the neutron star that the crust itself experiences severe mechanical strain. As the magnetic field lines continuously twist and realign through the magnetar's interior, they can fracture the rigid star crust in a catastrophic event known as a starquake. When the crust snaps, vast amounts of stored magnetic energy are instantly released into space, triggering a massive flare of high-energy X-rays and gamma radiation. A single giant flare from a magnetar can release more energy in a fraction of a second than our Sun produces over hundreds of thousands of years. In 2004, a giant flare from the magnetar SGR 1806-20, located 50,000 light-years away on the far side of the Milky Way galaxy, was so intense that it physically ionized Earth's upper atmosphere and saturated satellite detectors, demonstrating the terrifying reach of these magnetic monsters. While magnetar flares represent localized blasts of high energy, the cosmos hosts an even more devastating energetic phenomenon: gamma-ray bursts, or GRBs. Gamma-ray bursts are the most luminous and powerful electromagnetic explosions in the universe since the Big Bang itself. These flash events emit high-energy photons across space, temporarily outshining everything else in the observable universe in gamma radiation. Discovered accidentally by military satellites monitoring nuclear testing during the Cold War, gamma-ray bursts are categorized into two distinct physical classes based on their duration and underlying progenitor systems: short-duration gamma-ray bursts and long-duration gamma-ray bursts. Short-duration gamma-ray bursts last less than 2 seconds, often occurring in a brief fraction of a second. Despite their fleeting nature, they unleash unimaginable energy. These short bursts are produced by catastrophic compact binary mergers, specifically the violent collision of two neutron stars, or a neutron star spiraling into a stellar mass black hole. As these hyperdense objects orbit each other, they radiate gravitational waves, losing orbital energy until they smash together at a significant fraction of the speed of light. The resulting cosmic collision, known as a killer nova, forms a newly born black hole surrounded by a rapidly accreting torus of nuclear matter. This merger triggers focused relativistic jets that blast through space, while the surrounding neutron-rich debris synthesizes massive quantities of heavy elements like gold and platinum. Long-duration gamma-ray bursts, which last from several seconds to several minutes, originate from a completely different cosmic event known as a collapsar. A collapsar occurs during the fatal collapse of an extremely massive, rapidly spinning star that has lost its outer hydrogen and helium envelopes, known as a hypernova. When the core of such a massive star collapses directly into a black hole, the remaining stellar material falls inward at extreme speeds. If the star is rotating fast enough, the infalling gas forms a dense accretion disk around the newly created black hole. Relativistic jets of plasma are launched along the star's rotational axis, drilling through the collapsing stellar body and erupting out into space at nearly the speed of light. When these relativistic jets break free from the dying star, internal shockwaves within the jet convert kinetic energy into intense, highly focused beams of gamma radiation. Because the energy of a gamma-ray burst is focused into narrow twin beams rather than expanding uniformly in a sphere, any observer situated directly along the beam's line of sight witnesses an overwhelming flash of radiation across billions of light years. If a long-duration gamma-ray burst were to occur within our own galactic neighbourhood, situated just a few thousand light-years away with its beam pointed directly at Earth, the sudden bath of intense gamma-rays and ultraviolet light would destroy our planet's ozone layer. This would trigger global atmospheric chemical reactions, producing toxic nitrogen dioxide, blocking sunlight, and exposing surface life to deadly solar radiation, causing a mass extinction event. Through the physics of magnetars and gamma-ray bursts, the cosmos demonstrates its capacity to channel gravitational and magnetic forces into hyperconcentrated beams of radiation. These energetic flashes act as cosmic beacons, allowing astrophysicists to study stellar deaths and neutron star collisions at the absolute edge of the observable universe. Floating through the cosmic sea is our home galaxy, the Milky Way, a vast and complex island of stars, gas, dust, and dark matter that spans approximately 100,000 light-years across. From our perspective deep within one of its spiral arms, the Milky Way appears as a luminous milky band of light stretching across the night sky, an optical illusion created by viewing the flattened disk of our galaxy edge-on. To truly understand our place in the universe, we must step back and analyze the structural anatomy of this massive barred spiral galaxy, exploring its intricate architecture, its dynamic stellar populations, and the invisible scaffolding that maintains its cohesion against the vast forces of cosmic expansion. At the very structural center of the Milky Way lies the galactic core, a densely packed region dominated by millions of old, evolved stars orbiting within a bright central bulge. Emerging from this central bulge is a prominent linear feature known as the galactic bar, composed of ancient red stars and dense interstellar gas. This central bar acts as a gravitational engine, channeling gas and dust inward toward the galactic nucleus and driving orbital resonance patterns throughout the entire galactic disk. Nestled at the precise dynamic center of this central bar, roughly 26,000 light-years away from Earth, resides Sagittarius A star, a supermassive black hole containing over 4 million times the mass of our Sun. Sagittarius A star sits at the center of a chaotic region where stars orbit at blinding speeds, held in tight elliptical trajectories by its immense gravitational pull. Radiating outward from the central bar is the galactic disk, a relatively thin rotating plane of matter containing the vast majority of the galaxy's stars, gas clouds, and open star clusters. The disk is organized into several grand spiral arms, major structures such as the Perseus arm and the Scutum Centaurus arm, alongside smaller arm segments like the Orion Cygnus arm, where our solar system is located. These spiral arms are not rigid physical structures that rotate like the spokes of a bicycle wheel. Rather, they are density waves, moving regions of higher gravitational pressure that compress interstellar gas and dust as they sweep through the disk. As gas clouds pass through these galactic density waves, the compression triggers large-scale gravitational collapse, initiating bursts of new star formation. Consequently, the spiral arms glow brightly with short-lived massive blue stars, brilliant emission nebulae, and youthful star clusters, defining the luminous skeleton of our galaxy. Surrounding the main disk and central bulge is the galactic halo, a vast spherical region extending hundreds of thousands of light-years into space. The halo contains a much sparser population of extremely old metal-poor stars, often organized into tightly bound spherical groups known as globular clusters. These ancient globular clusters, containing hundreds of thousands of stars packed closely together, represent some of the oldest surviving objects in the universe, dating back to the earliest stages of galactic assembly, billions of years ago. Unlike stars in the disk, which orbit the galactic center in orderly, near-circular paths within the galactic plane, halo stars and globular clusters move in random, highly inclined eccentric orbits that crisscross the galaxy from all directions. However, as astronomers began measuring the orbital velocities of stars in the galactic disk during the mid-20th century, they stumbled upon a profound physical paradox that fundamentally altered our understanding of cosmology. According to the classical laws of Newtonian mechanics, and Kepler's laws of planetary motion, the orbital speed of an object orbiting a central mass should decrease with distance. Just as Mercury orbits the Sun much faster than Neptune, stars located far from the luminous centre of the Milky Way were expected to move significantly slower than stars orbiting closer to the core, because most of the visible mass, stars, gas and dust, appeared concentrated near the galactic centre. When observational astronomers, led by pioneering researchers like Vera Rubin, mapped the rotational speeds of stars and hydrogen gas clouds extending out to the visible edges of the Milky Way and other spiral galaxies, they discovered something completely unexpected. Instead of dropping off at greater distances, the galactic rotation curves remained flat. Stars orbiting at the outer fringes of the galaxy, tens of thousands of light-years from the centre, were travelling at virtually the same high velocities as stars near the inner core. According to standard physics, the gravitational pull generated by all the visible matter in the galaxy, every single star, planet, gas cloud and dust grain combined, is nowhere near strong enough to keep these fast-moving outer stars bound in their orbits. Based purely on visible mass, the outer regions of the Milky Way should be flying apart, scattering its stars into intergalactic space. Yet, the galaxy remains intact, spinning steadily without tearing itself to shreds. This revealed that the Milky Way and other galaxies must be embedded within a massive, invisible halo of unknown matter, whose gravitational force provides the extra glue holding everything together. This mysterious, non-luminous mass is known as dark matter. Observations indicate that dark matter makes up roughly 85% of all the matter in the universe, outnumbering normal baryonic matter, the stuff that makes up stars, planets, trees and human beings, by a ratio of more than 5:1. Dark matter does not emit, absorb, reflect or refract light or any other form of electromagnetic radiation across any spectrum. It does not interact with the electromagnetic force, meaning it cannot form atoms, molecules or solid objects, nor does it collide with normal matter in any traditional sense. Its existence is inferred entirely through its gravitational effects on visible matter, light, and the large-scale structure of the cosmos. To explain the flat rotation curves of galaxies, astrophysics dictates that dark matter forms an enormous, diffuse, spherical envelope known as a dark matter halo that extends far beyond the visible boundaries of the stellar disk. In the Milky Way, this dark matter halo stretches out to hundreds of thousands of light-years, weighing down the galaxy and dictating the gravitational motion of its satellite dwarf galaxies, such as the Large and Small Magellanic Clouds. Without the deep gravitational wells created by these vast dark matter halos, primordial gas in the early universe would never have been able to collapse efficiently enough to form the first generations of stars and galaxies. In this sense, dark matter served as the essential cosmic framework, the invisible scaffolding around which all visible cosmic structures assembled. Determining the fundamental particle nature of dark matter remains one of the greatest unsolved quests in modern physics. Physicists have proposed several theoretical candidates to explain this mysterious substance. For decades, one prominent hypothesis centered on weakly interacting massive particles, often called WIMPs. These are hypothetical subatomic particles that possess mass and interact through gravity and potentially the weak nuclear force, but remain completely immune to electromagnetism and the strong nuclear force. If weakly interacting massive particles exist, billions of them are passing harmlessly through your body and the entire Earth every second, without leaving a trace or colliding with a single atomic nucleus. Another leading candidate is the axion, an extremely lightweight hypothetical elementary particle originally proposed to solve theoretical problems in quantum chromodynamics. Axions, if real, would have been produced abundantly during the Big Bang, forming a cold, ultralight Bose-Einstein condensate of dark matter filling the universe. Other exotic possibilities include sterile neutrinos, heavy hypothetical partners to known subatomic particles, or even primordial black holes created during the ultra-dense first moments of the Big Bang before stars ever existed. Despite decades of sophisticated experiments conducted in deep subterranean laboratories, shielded beneath kilometers of solid rock, Using ultra-sensitive liquid xenon detectors and advanced particle accelerators, scientists have yet to directly detect a single dark matter particle. Yet, its gravitational presence is undeniably etched across the cosmos. We observe dark matter bending the light of distant galaxies through gravitational lensing, shaping the cosmic microwave background radiation and dictating the motion of vast galaxy clusters. In the grand cosmic hierarchy, our Milky Way galaxy is far more than a simple collection of glowing stars. It is an intricate ecosystem where matter is endlessly recycled, born in gas clouds, fused inside stellar cores, blasted out in supernova explosions, and swept up into new planetary systems. Yet, all of this visible beauty, every glittering star and sweeping spiral arm, is merely a thin skin of luminous dust floating within a vast invisible ocean of dark matter. It is this silent, phantom mass that dictates our galactic rotation, guards our solar system from drifting into the void, and maintains the structural integrity of our cosmic island. Zooming out beyond the dark matter halo of the Milky Way, our perspective expands into intergalactic space, where galaxies themselves cease to appear as isolated entities. Instead, galaxies assemble into bound gravitational structures, ranging from small groups to colossal clusters containing thousands of members. Our home galaxy resides within a relatively modest intergalactic neighborhood known as the local group. Spanning roughly 10 million light-years across, the local group is a gravitational collection of more than 80 identified galaxies, dominated by two colossal spiral titans, our own Milky Way and our giant neighbor, the Andromeda galaxy, also catalogued as Messier 31. While the local group contains dozens of smaller dwarf galaxies, such as the Large and Small Magellanic Clouds, the Draco Dwarf and the Fornax Dwarf, the overarching gravitational dynamics of our local cosmic neighborhood are dictated almost entirely by the interaction between the Milky Way and Andromeda. Located approximately 2.5 million light-years away, Andromeda is the largest galaxy in our immediate vicinity, spanning over 200,000 light-years across and housing an estimated 1 trillion stars, more than double the stellar population of the Milky Way. Like our galaxy, Andromeda is a grand spiral galaxy with a prominent central bulge, a supermassive black hole at its core, and a vast surrounding dark matter halo. For billions of years, the Milky Way and Andromeda have been drifting through the cosmic void, but they are not moving apart. While the universe as a whole is expanding, with distant galaxies receding from one another at accelerating speeds, the local gravitational pull between neighboring galaxies can easily overcome this universal expansion on smaller scales. Bound together by their massive dark matter halos, the Milky Way and Andromeda are locked in a relentless gravitational embrace, drawing closer to each other at a blistering speed of approximately 110 kilometers per second, or nearly 400,000 kilometers per hour. Precise measurements of Andromeda's transverse and radial motion, gathered using advanced space telescopes, have confirmed a dramatic cosmic destiny. The Milky Way and Andromeda are on an absolute, unavoidable, head-on collision course. In approximately 4 to 5 billion years, these two galactic giants will meet, initiating a spectacular cosmic transformation that will forever alter the structure of our local universe. As the two galaxies approach one another, their surrounding dark matter halos will be the first structures to interact, merging and generating immense tidal friction that slows down their relative orbital speeds. As the visible stellar disks slam into each other, the gravitational forces will distort their beautiful spiral structures. Long dramatic streams of stars, gas and dust, known as tidal tails, will be ripped away and flung hundreds of thousands of light-years out into intergalactic space. Despite the terrifying scale of this collision, actual physical collisions between individual stars will be extraordinarily rare. Galaxies are mostly empty space. The distances between individual stars within a galaxy are so vast that two colliding galaxies pass through each other like ghosts, with stars simply sliding past one another within newly distorted gravitational paths. However, the vast interstellar gas clouds within both galaxies will collide head-on. As giant molecular clouds of hydrogen gas smash together at high velocities, The extreme pressure triggers widespread shockwaves throughout both systems. This leads to a galactic starburst, an intense period of hyper-accelerated star formation, where millions of new stars ignite across the merging system simultaneously. The night sky during this phase would be illuminated by vast, glowing pink emission nebulae and clusters of brilliant, short-lived blue giant stars. This initial pass will not immediately unify the two galaxies. Instead, momentum will carry them apart for a brief cosmic moment before gravity pulls them back together for a second, even more violent encounter. Over the course of 1 to 2 billion years, as orbital energy is transferred into the dark matter halo and dispersed through tidal interactions, the distinct spiral arms of both the Milky Way and Andromeda will be completely erased. The organized rotating disks will dissolve into a chaotic three-dimensional cloud of stars moving in random eccentric orbits. At the center of this merging system, the two supermassive black holes, our Sagittarius A star and Andromeda's even larger central black hole, will sink toward the newly forming common gravitational center through a process known as dynamical friction. As these two giant black holes orbit one another at ever-decreasing distances, they will stir up surrounding gas, potentially igniting new quasar-like active galactic nuclei. Eventually, as the binary black holes spiral inward to within light days of each other, they will radiate intense gravitational waves through the fabric of space-time, losing the last of their orbital energy and merging into a single, colossal, supermassive black hole. The ultimate outcome of this multi-billion-year collision will be the birth of a giant, smooth, featureless, elliptical galaxy, often referred to by astronomers as Milkomeda. The gas clouds will have been largely consumed by the initial starburst, or blown away into intergalactic space by supernova explosions, bringing an end to active star formation. Milkomeda will mature into a quiet, reddish galaxy dominated by older, low-mass stars, drifting peacefully through the local group. By the time this merger completes, our Sun will have evolved into an expanding red giant, rendering Earth uninhabitable long before the final galactic fusion occurs. However, if any intelligent observers exist in the outer reaches of the solar system or on distant worlds during that far future era, they will witness a night sky transformed from a single milky band into a dazzling three-dimensional sphere of billions of ancient stars, marking the triumphant conclusion of our local galactic evolution. Expanding our vision far beyond the local group, the individual identity of galaxies fades into a much grander, breathtaking cosmic pattern. When viewed on scales of hundreds of millions of light years, the universe reveals an intricate, web-like architecture known as the cosmic web. This colossal framework is the largest coherent structure in existence, a vast three-dimensional network composed of interconnected filaments of dark matter, gas, and galaxies surrounding unimaginable expanses of empty space. Within this cosmic web, gravity and dark matter have arranged billions of galaxies into a defined structural hierarchy: nodes, filaments, superclusters, and cosmic voids. At the densest intersections of these cosmic filaments sit galaxy clusters and superclusters, the absolute heavyweights of the universe. Galaxy clusters are gravitationally bound structures containing hundreds or even thousands of individual galaxies immersed in a sea of superheated intergalactic gas and shrouded within massive dark matter halos. Clusters themselves group together into even larger structures called superclusters, which span hundreds of millions of light-years across. Our local group lies in the wider region of the Virgo supercluster. On an even larger scale, this region forms part of an incomparably vast cosmic home, the Laniakea supercluster. Spanning over 500 million light-years and containing the mass of 100 quadrillion suns, Laniakea, a name evoking immense heavens, defines our true cosmic address. Within Laniakea, hundreds of thousands of galaxies are all flowing along gravitational pathways toward a central gravitational anomaly known as the Great Attractor, a massive concentration of dark matter and galaxy clusters that pulls everything in our local region of the universe toward its dense core. Threading between these massive superclusters are cosmic filaments, long bridges of dark matter and diffuse gas along which galaxies migrate over cosmic time. These filaments act as the superhighways of the universe, channeling gas and matter into the superclusters at their nodes. Dark matter acts as the primary gravitational backbone for these filaments, drawing normal baryonic gas inward through its deep gravitational potential wells and allowing galaxies to form and cluster along these invisible cosmic threads. Yet, what makes the cosmic web truly extraordinary is not just where matter exists, but where it is completely absent. Settled between the luminous filaments and dense superclusters lie the great voids, immense, spherical regions of space that are virtually devoid of galaxies, dark matter, or baryonic gas. These cosmic voids are the vast deserts of the universe, spanning anywhere from tens of millions to over 300 million light-years across. The most famous of these empty realms is the Bootes Void, often referred to as the Great Nothing. Spanning roughly 330 million light-years in diameter, the Bootes Void is so vast that if the Milky Way had been located at its center, humanity would not have discovered the existence of other galaxies until the advent of ultra-powerful telescopes in the late 20th century. While a region of space that size should normally contain tens of thousands of galaxies based on average cosmic density, the Bootes Void contains only a tiny handful of isolated, lonely galaxies drifting in absolute solitude. The origin of this colossal, web-like distribution dates back to the very first fraction of a second following the Big Bang. During the epoch of cosmic inflation, the ultra-early universe expanded exponentially, stretching subatomic quantum fluctuations in the fabric of spacetime up to astronomical scales. These quantum variations created microscopic density differences in the primordial plasma, tiny regions that were slightly denser or slightly less dense than the cosmic average. As the universe cooled and expanded, gravity began amplifying these initial density variations. The slightly denser regions exerted a stronger gravitational pull, gradually drawing in surrounding dark matter and gas over billions of years, growing into the dense filaments, galaxy clusters, and superclusters we observe today. Conversely, the slightly less dense regions lost matter to the surrounding gravitational strongholds, emptying out over time to become the vast cosmic voids. Cosmic voids are far from useless empty space. They offer cosmologists an extraordinary laboratory for testing fundamental physics. Because voids are nearly free from the complex gravitational interactions, supernova feedback, and dense dark matter concentrations that dominate galaxy clusters, the space inside a void represents a pristine environment dominated almost entirely by dark energy. By measuring the precise shapes, expansion rates, and light-bending properties of these empty cosmic bubbles, astronomers can map the acceleration of the universe and probe the fundamental nature of the vacuum itself. When mapped in 3 dimensions by modern astronomical sky surveys, the cosmic web resembles a vast, glowing neural network or a delicate foam structure floating through eternity. Galaxies are not scattered randomly through space like dust floating in the air. They are locked into this dynamic, evolving framework, riding along dark matter filaments and surrounding vast bubbles of empty space. On this grandest of all observable scales, individual solar systems and even entire galaxies become tiny illuminated specks marking the threads of a grand cosmic tapestry that stretches across the infinite expanse of space and time. To comprehend the grand architecture of the cosmic web, the life cycles of stars and the behavior of exotic entities like black holes, we must abandon the intuitive, everyday understanding of reality that governs human experience. For centuries, classical physics framed space as a static, unyielding stage upon which cosmic events unfolded, and time as a uniform, universal clock ticking at an absolute, unalterable rate across the entire universe. This Newtonian worldview was remarkably effective for calculating planetary orbits and terrestrial motion, but it obscured a far deeper, more mysterious truth about the universe. At the dawn of the 20th century, Albert Einstein revolutionized physics by demonstrating that space and time are not independent, rigid concepts. Instead, they are intimately fused into a dynamic 4-dimensional continuum known as spacetime. 3 dimensions of space, height, width, and depth, are inextricably bound to a 4th dimension, time. Space-time is not a passive backdrop. It is a physical, flexible fabric that can bend, stretch, warp, ripple and twist under the influence of mass and energy. This profound insight forms the foundation of Einstein's theory of general relativity, which completely redefined our understanding of gravity. In classical mechanics, gravity was viewed as an invisible attractive force pulling instantly between two distant masses across space. General relativity revealed that gravity is not a traditional force at all, rather it is a direct geometric consequence of the curvature of spacetime. When mass or energy is introduced into a region of spacetime, it creates a local depression, warping the geometry around it. Think of a heavy bowling ball resting upon a stretched rubber sheet. The heavy ball depresses the material, causing the surrounding fabric to curve downward. If you then roll a marble across the sheet, the marble does not travel in a straight line, it follows a curved path dictated by the dip created by the bowling ball. In the cosmos, massive objects like stars, planets, and black holes warp the four-dimensional fabric of space-time around them. Planets orbiting the Sun are not being drawn inward by an invisible tether. They are simply following the shortest, most natural path, known as a geodesic, through a curved four-dimensional space-time environment carved out by the immense mass of the Sun. Because gravity is the curvature of space-time itself, it affects everything travelling through that curved geometry, including light. Although photons of light possess no rest mass, they are bound to follow the geometric contours of space-time. When light emitted by a distant star or galaxy passes close to a massive foreground object, such as a galaxy cluster or a supermassive black hole, the light path is bent by the warped space-time surrounding that massive lens. This phenomenon is known as gravitational lensing. Gravitational lensing serves as one of the most brilliant observational tools in modern astrophysics. When a massive foreground galaxy cluster sits directly along our line of sight to a much more distant background galaxy, the cluster's immense gravity acts as a colossal cosmic magnifying glass. The light from the background object is deflected, magnified, and distorted as it travels through the curved space-time around the cluster. Depending on the precise alignment and mass distribution of the foreground lens, gravitational lensing can split the light of a single distant background galaxy into multiple distinct images, arc-like arcs, or even a complete glowing halo of light, known as an Einstein ring. Weak gravitational lensing, which causes subtle geometric distortions in the apparent shapes of distant galaxies, allows astronomers to map the distribution of invisible dark matter throughout galaxy clusters and the cosmic web, tracing mass that would otherwise remain completely undetectable. Strong gravitational lensing magnifies extremely faint early galaxies that existed during the cosmic dawn, allowing space telescopes to peer deeper into the universe's history than would ever be possible using optical lenses alone. Yet, space-time curvature does not merely bend spatial paths, it fundamentally warps the flow of time itself through a mind-bending physical reality known as gravitational time dilation. The stronger the gravitational field, or the more severely space-time is curved by mass, the slower time ticks relative to an observer situated in a weaker gravitational field. If you were to stand on the surface of a hyperdense neutron star, where gravity is hundreds of billions of times stronger than on Earth, your clock would tick noticeably slower compared to a clock floating in deep intergalactic space far from any mass. Near the event horizon of a supermassive black hole, where space-time curvature approaches extreme limits, gravitational time dilation becomes astounding. To a distant observer watching an astronaut fall toward a black hole, the astronaut's clocks would appear to slow down continuously, their movements frozen into ultra-slow motion, and the light emitted from their suit shifted to longer, redder wavelengths until they seemed to freeze permanently at the edge of the event horizon. From the astronaut's personal frame of reference, however, their local clock ticks completely normally as they plunge across the boundary in a finite amount of personal time. Gravitational time dilation is not merely a theoretical concept reserved for black holes, it is an everyday reality measured precise atomic clocks. Clocks located at sea level on Earth, closer to the planet's gravitational core, run measurably slower than identical atomic clocks positioned on high mountain peaks or orbiting onboard satellites in space. Space-based global positioning systems must continuously account for both the time dilation caused by their high orbital velocities and the gravitational time dilation caused by Earth's mass curve. Without applying relativistic mathematical corrections derived from general relativity, global satellite navigation systems would accumulate errors of several kilometers every single day, rendering modern location technology completely non-functional. Furthermore, general relativity predicts that when massive objects undergo acceleration, they generate dynamic ripples that propagate outward through the fabric of spacetime itself at the exact speed of light. These ripples are gravitational waves, produced by some of the most energetic events in the cosmos, such as the violent merger of two spiraling black holes, colliding neutron stars, or asymmetric supernova explosions. Gravitational waves squeeze and stretch space itself as they pass through spacetime. When a gravitational wave passes through Earth, it physically stretches space in one transverse direction, while compressing space in the perpendicular direction, altering distances by a fraction far smaller than the diameter of a single atomic proton. The detection of these elusive spacetime ripples by ultra-precise laser interferometers marked a monumental breakthrough in modern science. By measuring the subtle physical stretching of laser paths kilometers long, scientists unlocked a completely new sensory modality for exploring the universe. Rather than merely viewing the cosmos through electromagnetic light across optical, radio, or X-ray spectrums, we can now listen directly to the violent vibrations of spacetime itself as black holes smash together in the dark. Spacetime also demonstrates extraordinary flexibility on a cosmological scale through the physics of universal expansion. As the universe expands, it is not a case of galaxies flying outward through static space like shrapnel from an explosion. Instead, space itself is expanding between unbound galaxy clusters. The physical distance between distant galaxies increases because the underlying metric of spacetime is stretching. As light travels across billions of light-years of stretching spacetime to reach our telescopes, the wavelength of the light itself is stretched along with the spatial metric, shifting the light toward longer, redder wavelengths. This phenomenon, known as cosmological redshift, is distinct from the traditional Doppler effect and provides direct physical evidence that the four-dimensional manifold of our universe has been continuously expanding since its creation. The true nature of spacetime reveals that physical reality is far more interconnected, flexible, and dynamic than human intuition suggests. Space and time are not fixed, separate dimensions, but a unified, malleable continuum warped by energy and mass. From the subtle time shifts affecting our daily satellite technology to the dramatic light bending around galaxy clusters and the gravitational wave tremors radiating from merging black holes, the curvature of spacetime serves as the foundational language through which the universe conducts its physical phenomena. To truly grasp the story of the universe, we must journey back to the absolute beginning of space, time, and matter, and then project our vision forward to the ultimate destiny of the cosmos. Everything we observe today, from the smallest subatomic particles to the grandest galaxy superclusters, originated from a single, infinitely hot, infinitely dense point known as the initial singularity. Approximately 13.8 billion years ago, this singularity underwent an event that set reality in motion, the Big Bang. The Big Bang was not an explosion of matter bursting into pre-existing empty space. Instead, it was the explosive creation and rapid expansion of spacetime itself. In the first, unimaginably tiny fraction of a second, during an epoch known as cosmic inflation, the universe expanded exponentially, stretching quantum fluctuations up to astronomical scales. As the newborn cosmos expanded, it cooled rapidly, transitioning from an ultra-dense sea of pure energy into a plasma of fundamental particles, quarks, gluons, and leptons. Within the first few minutes after the Big Bang, a period known as Big Bang nucleosynthesis occurred. As temperatures dropped to roughly 1 billion degrees Celsius, protons and neutrons fused together to forge the lightest atomic nuclei, hydrogen, helium, and trace amounts of lithium. However, the universe remained an opaque, glowing fog. Free, unattached electrons constantly scattered photons of light, preventing radiation from traveling freely through space. This cosmic obscurity persisted for approximately 380,000 years, until the expanding universe cooled down to roughly 3,000 degrees Celsius. At this critical juncture, known as the recombination epoch, the thermal energy dropped low enough for atomic nuclei to capture free electrons, forming the first neutral hydrogen and helium atoms. With free electrons bound into stable atoms, space suddenly became transparent to electromagnetic radiation. The photons that were liberated during recombination broke free and began traveling unimpeded across the expanding cosmos. Today, 13.8 billion years later, we still detect this primordial light as a faint, uniform glow coming from every direction in the sky, the cosmic microwave background radiation, or CMB. Because space-time has stretched dramatically since the early universe, these ancient high-energy photons have been stretched into longer microwave wavelengths, arriving at Earth at a cold temperature of just 2.7 degrees above absolute zero. The cosmic microwave background serves as the ultimate baby picture of the universe, preserving tiny temperature fluctuations that reflect the initial seeds of matter from which all future cosmic structures grew. For hundreds of millions of years following recombination, the universe entered the cosmic dark ages. No stars shone, and no galaxies illuminated the dark hydrogen gas filling space. Gradually, gravity drew matter into denser regions dictated by dark matter halos, eventually igniting the first generation of massive stars and lighting up the cosmos. For billions of years, the universal expansion driven by the Big Bang was expected to gradually slow down over time due to the collective gravitational pull of all the matter in the universe. Scientists assumed that gravity would act as a cosmic brake, slowly decelerating the outward expansion of galaxies. However, in 1998, observations of distant Type 1a supernovae yielded a shocking discovery that transformed cosmology. Instead of slowing down, the expansion of the universe is actually accelerating. Something in the fabric of space is exerting a repulsive force, pushing galaxies apart at an ever-increasing rate. This mysterious phenomenon, driving cosmic acceleration, is known as dark energy. Dark energy constitutes roughly 68% of the total mass energy content of the universe, dominating over both normal baryonic matter and dark matter combined. Unlike matter, which dilutes and weakens in density as space expands, dark energy appears to maintain a constant energy density per unit volume of space, functioning like a cosmic constant embedded within the vacuum of spacetime itself. The fundamental nature of dark energy remains one of the paramount unsolved questions in theoretical physics. One leading explanation is the cosmological constant, an idea originally introduced by Albert Einstein, which posits that dark energy is an intrinsic property of space itself, a vacuum energy that generates a negative pressure, driving space to expand faster as more space is created. Another hypothesis suggests quintessence, a dynamic, time-evolving energy field that permeates the cosmos. The competition between the attractive force of gravity and the repulsive acceleration of dark energy dictates the ultimate fate of our universe. Cosmologists have modeled several possible scenarios for how the cosmos will end, depending on the precise physical properties and behavior of dark energy over deep cosmic time. One potential scenario is the Big Crunch. If the density of dark energy were to decrease over time, or reverse its behavior, the gravitational pull of all the matter in the universe could eventually overcome the expansion. In this scenario, the expansion would reach a peak, halt, and reverse direction. Galaxies would begin racing back toward one another. Space-time would contract, and all stars, planets, and matter would be crushed together into a hyperdense, high-temperature furnace, culminating in a violent singularity reminiscent of the Big Bang in reverse. Conversely, if dark energy increases in strength over time, a form known as phantom dark energy, the cosmos could face a catastrophic end known as the Big Rip. As dark energy grows progressively stronger, the accelerating expansion rates would become so extreme that it would overcome all structural forces binding matter together. First, galaxy superclusters would be torn apart, followed by individual galaxies and solar systems. As the rip progressed to its final moments, planets would be ripped from their orbits, atomic structures would be torn apart, and space-time itself would shred into an infinite singularity of infinitely expanding points. However, based on current observational data, the most widely accepted and probable long-term forecast for our universe is the heat death, also known as the Big Freeze. In this scenario, dark energy continues to drive universal expansion at a steady, accelerating pace forever. As galaxies are pushed farther and farther apart, they will eventually recede beyond our observable horizon, isolating galactic island groups in an ever-growing expanse of empty void. Over trillions of years, the supply of interstellar gas within galaxies will be fully exhausted. No new stars will ignite, and existing stars will slowly burn out one by one. Massive blue giants will die first, followed by medium stars like our Sun, until only cold white dwarfs, dim red dwarfs, and dead neutron stars remain. Red dwarfs will slowly exhaust their nuclear fuel, fading into dark, inert black dwarfs. Eventually, even the black dwarfs and dead stellar remnants will disintegrate. According to theories of grand unification, protons themselves may slowly decay over vast cosmic timescales, causing solid atomic matter to dissolve into elementary particles. During this far future epoch, black holes will reign supreme as the final macroscopic structures in the universe. Yet, even black holes are not eternal. Through a quantum mechanical process known as Hawking radiation, black holes slowly evaporate by radiating virtual particles into space. Over unimaginable timespans, stretching across hundreds of trillions of years, supermassive black holes will gradually lose mass and evaporate in final, subtle flashes of high-energy radiation. Once the last black hole has evaporated, the universe will enter a state of maximum entropy and thermal equilibrium. The cosmos will become a vast, cold, dark, and uniform sea of low-energy photons, leptons, and neutrinos, drifting through an infinitely expanding void. No thermodynamic work can be performed, no structures can form, and virtually no physical processes can mark the passage of time. The universe will have reached its absolute thermal end, drifting peacefully through an eternal, motionless twilight. Standing at the edge of this unimaginable cosmic expanse, looking across billions of light-years of space and time, it is easy to feel small and insignificant. We occupy a tiny, fragile world, a pale blue dot drifting through an endless ocean of stars, governed by immense forces of energy, dark matter, and eternal expansion. Yet, our true significance lies not in our physical size, but in our capacity to comprehend this vast reality. Through curiosity, mathematics, and science, we are the universe observing, understanding, and contemplating itself. We are star stuff that has come alive to decipher the very laws that forged the cosmos. If you enjoyed this unforgettable journey through the universe, please feel free to like this video and subscribe to the channel for more cosmic explorations. We would love to hear your thoughts, so please leave a comment below sharing where on Earth and at what time you are watching this today.